Some of the most important applications of differential calculus are optimization problems, in which we are required to find the optimal or best way of doing something. These are just some examples. What is the shape of a can that minimizes manufacturing cost? What is the maximum acceleration of a space shuttle? What is the radius of a contracted windpipe that expels air most rapidly during a cough? At what angle should blood vessels branch so as to minimize the energy expended by the heart in pumping blood? This will be the guidelines for solving optimization problems. Identify all given quantities and quantities to be determined. Make a sketch and label the quantities. Write a primary equation for the quantity that is to be maximized or minimized. Reduce the primary equation to one having a single independent variable. Determine the feasible domain of the primary equation. Determine the desired maximum or minimum value by using calculus techniques. Find two numbers whose sum is 20 if the product of one by the cube of the other is to be maximum. So let's now write the given. We have two numbers, so that would be x and y. And their sum is 20. So x plus y equals 20. So from this, we can get the value of x. So the value of x now is equal to 20 minus y. So what would be the required? We have to find the two numbers. So the unknown now would be x and y. So what is the other given? That the product of one by the cube of the other is to be maximum. So the product of one, that would be x, by the cube of the other, so y cube, is to be maximum. So we can now substitute the value of x from here. So we have x, so that would be 20 minus y, and then y cube. So what would now be this value? So our working equation now is 20 y cube minus y times y cube, that would be y raised to 4. So since we already have one variable, we can now differentiate this with respect to y. So the derivative now of p with respect to y is, this is 60 y squared minus 4y cubed. And since the product is maximum, so dp over dy is equal to 0. So we can now have that. So that would be equal to 0. So what would be our value now? Okay. So 60 y squared minus 4y cubed equals 0. We can factor out 4 and also y squared. So what would be this value? So this is now 15 minus y equals 0. So we have two values of y. The first one is 4y squared equals 0. So the value of y would be 0. And then the other one is 15 minus y equals 0. So y is positive 15. So one number is 15. So we can now compute for the value of x from this given. So x is equal to 20 minus y. So x now is equal to 20 minus 15. So we have 5. So these are now the numbers. So we have 5 and 15. Another example, a rectangular field of area 1,000 square meters is to be fenced off along the river, along the bank of the river. If no fence is needed along the river, what is the dimension of the field requiring the least amount of fencing? So we have a rectangular field, and it is along the bank of the river. So no fencing is needed along the bank of the river. So let's designate this as x, and then this would be y, and then another y. Okay? What is the dimension of the field requiring the least amount of fencing? So what would be the least or the minimum perimeter? And we have a given area. Okay? So what would be the required? The required would be the dimensions of the rectangular field. So we will be needing the perimeter. The perimeter of this is x plus y plus y. So that would be x plus 2y. But we have two variables. We just need one single independent variable. So let's use the value of the area. So area is given as 1,000 square meters and the area of this rectangle is xy. So let's solve for the value of x. It's 1,000 over y. So we can now substitute this x with this. So x is 1,000 over y plus 2y. Let's differentiate now with respect to y. Derivative of p with respect to y. 1,000 over y is equal to 1,000 y raised to negative 1. So the derivative of that is negative 1,000 y raised to negative 2 or negative 1,000 over y squared. Derivative of 2y is 2. And then since least amount of fencing, so we will be having a minimum perimeter. So dp over dy now is equal to 0 since the perimeter is minimum. Okay? So we can now substitute the value of dp over dy and then we will equate that to 0. So this is the value. Negative 1,000 over y squared plus 2 equals 0. Transpose that one. So we have 1,000 over y squared equals positive 2 and then transpose. So we now have y squared which is 1,000 over 2 or 500. So how can we have the value of y? We'll just get the square root of 500. So it would lead to positive and negative values. Okay, so which is 10 square root of 5. But since it is dimension and we don't have any negative value for dimension, same with the area and volume, so we will be taking the positive value. So with that, we can now write the value of y, which is positive 10 square root of 5 meters. Solving for x. X is equal to 1,000 over y. So 1,000 over 10 square root of 5. So the value of x now is 20 square root of 5 meters. So the dimension now of the rectangular field is 10 square root of 5 meters by 20 square root of 5 meters. Another given. A triangular corner lot has perpendicular sides of length 120 feet and 160 feet. Find the dimensions of the largest rectangular building that can be constructed on the lot with sides parallel to the streets. So we have a rectangular lot and its dimensions would be 120 feet and 160 feet. Now, a rectangular building is to be constructed on the given lot with sides parallel to the streets. So this would now be the rectangular lot in which it has a dimension. So we have x and y. So the required now would be the dimensions of the rectangular lot. So that would be xy. So we'll now be needing the area of a rectangle. So the area of a rectangle is length times width. So that would be x times y. But we have two variables here. So we just need to express one variable in terms of the other. So let's use this triangle. So the bigger triangle, this is 120 and then this is 160. And then for the smaller triangle, you can use this one or the other one. So let's use this one. We have height. And then this is a total of 160. This is x. So this is 160 minus x. So by using ratio and proportion, so we have 120 over 160. And this is equal to y over 160 minus x. We can solve for the value of y. Y is equal to 120 over 160. And then transpose that. 160 minus x, which has a value of 120 minus 120 over 160. So that would be 3 over 4x. So that is now the value of y. So let's substitute that with our area. So what would be our area now? So area is x and then the value of y is this. 120 minus 3 over 4 x. Let's distribute the value of x. So we have 120x minus 3 over 4 x squared. And then we can now differentiate this one. Okay? So let's differentiate this with respect to x. dA over dx. We have 120 minus, so this would be 6 over 4 x. Okay? So after that, since the given is largest rectangular building, so the area is maximum. So we can now equate this to 0. So 120, 3 over 4, 6 over 4 is 3 over 2. So 3 over 2x equals 0. So we can now solve for the value of x. Transpose this one, it would become positive, and then 120 divided by 3 over 2. Okay, so this is 120 all over 3 over 2. So what would be the value of x now? You will come up with a value of 80. So x is 80 feet. We can now solve for the value of y from here. So y is equal to 120 minus 3 over 4. The value of x is 80. So solving for that, y is 60 feet. So we can now write the dimension. So the dimensions now of the rectangular lot is x by y. So that would be 80 feet by 60 feet. Okay, so another given for optimization problems. Find the volume of the largest box that can be made by cutting out equal squares of the corners of a piece of cardboard of dimensions 15 inches by 24 inches and then turning up the sides. Okay, so we have a piece of cardboard and the dimensions of that cardboard is 15 inches by 24 inches. So this is 15, this is 24. Next, we are to cut out squares. And we don't know that dimension, so let's designate that as x by x. And now, we will cut the squares and then we'll turn up the sides. Then, eventually, we will be having an open box. Okay? So with this open box, we have the height, that would be x, and then for this value, this is x, another x, so this would be 15 minus 2x, and then 24 minus x and x, so 24 minus 2x. So largest box, so it means that it would be the volume of the largest box. So what would be the required? The required is the volume. So let's now solve for the volume. So volume is length times width times height. So we have x times 24 minus 2x times 15 minus 2x. So solving this, we will be having 360x minus 78x squared plus 4x cubed. So since the given is expressed in single independent variable, so we can now differentiate the volume with respect to x. So differentiating, we have 360 and then negative 156x plus 12x squared. So since the volume is maximum, we can equate dv over dx to 0. So dv over dx now is equal to 0 since the volume is maximum. So let's have that. So we have 360 minus 156x plus 12x squared equals 0. We can still simplify this equation. So by dividing the whole equation by 12, the simplified equation now would be, let's arrange it, x squared minus 13x plus 30 equals 0. So solving for the values of x here, you will come up with the values of 10 and 3. So now, how are we going to know which would give the largest or the maximum volume? So we can use the second derivative test. Getting the second derivative of this, so the second derivative of the volume with respect to x, it's negative 156 plus 24x. So we have two values of x. At x equals 10, this is negative 156 plus 24. The value of x is positive 10. So we will come up with positive 84. So it is a positive value, so it's minimum. At x equals 3, same process. The value now of the second derivative is negative 156 plus 24 times 3. And we will be getting negative 84. So it means that at x equals 3, we'll be having a maximum volume. Let's solve for the volume. So the volume now, this is the formula for the volume. It's 360 times 3, negative 78, 3 squared plus 4, 3 cubed. So the volume, if you're going to solve for this, is 486 cubic inches. So that is the maximum volume. How about what if you will be using x as 10? Let's check. This is at x equals 3. So at x equals 10. So the volume is 360 times 10, negative 78, 10 squared, plus 4, 10 cubed. So you will get negative 200. And definitely there is no volume which is negative 200 because there is no negative volume. Rates or time rates. If we are pumping air into a balloon, both the volume and the radius of the balloon are increasing and the rates of increase are related to each other. But it is much easier to measure directly the rate of increase of the volume than the rate of increase of the radius. In related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity. This would be the guidelines in order to solve time rate or related rate problems. Identify all given quantities and quantities to be determined. Make a sketch and label the quantities. Write an equation involving the variables whose rates of change either are given or are to be determined. Using the chain rule, implicitly differentiate both sides of the equation with respect to time t. After completing guideline 4, substitute into the resulting equation all known values for the variables and their rates of change, then solve for the required rate of change. So let's have our given. A point moves on the parabola y equals x squared, so that its abscissa increases at a rate of 4 feet per second. At what rate is the ordinate increasing when x equals 2? So we have a given equation and that would be y equals x squared. It's the equation of the parabola. So at what rate is the ordinate increasing? So when we say ordinate, is the y. When we say abscissa, it's the x. So what would be the rate of the ordinate? So we need to get dy over dt. So since it's related rate, so we will be differentiating the given with respect to time. So let's solve this one. Given equation, y equals x squared. So let's now differentiate both sides of the equation with respect to time t. So dy over dt equals the derivative of x squared. So that would be 2x dx over dt. And then we will substitute the given. We have 2, the value of x when x is 2. So that would be 2 dx over dt. So the rate of the abscissa is 4 feet per second. So that would be 4 So this is a value of 16. So dy over dt now is 16 feet per second. At a certain instant, the dimensions of a rectangle are 8 and 12 feet, and they are increasing at the rates 4 and 3 feet per second respectively. How fast is the area changing? Okay, so we have a given rectangle. So if it is a rectangle, it has a length and a width. So let's designate this as x and then the vertical distance as y. How fast is the area changing? So we need to get dA over dt. So solving this, we need the area of a rectangle. So the area of a rectangle is length times width. So that would be x, y. Okay, so let's now differentiate this with respect to time. So we have dA over dt. Using product rule, we have x dy over dt plus y dx over dt. So let's now substitute the given. So the rectangle, the dimensions of a rectangle are 8 and 12 feet. So 8 would be for x and then 12 for y. So we have 8. And then the rate of the increase would be 4 for x and then 3 for y. So dy over dt now is 3 plus the value of y, that would be 12. Dx over dt is given as 4. And solving this one, we will be arriving with a value of 72 square foot per second. A kite at a height of 60 feet is moving horizontally at a rate 8 feet per second away from the boy who flies it. How fast is the cord being released when 100 feet are out? So we have a given kite. So let's say that this is the point where the boy stands, and then he has a kite, and the altitude is given as 60 feet. Now the kite is moving horizontally. Okay, so it moves horizontally. Let's designate that horizontal distance as x. So let's say this would be the position now of the kite. So we have dx over dt, and it is given as 8 feet per second. So it moves away from the boy. So it means that the value of x is increasing, so it's a positive rate of change. How fast is the cord being released when 100 feet are out? So let's designate the length of the cord as s. So there is no given for the rate of the height. So the height is constant. So what would be the required now? So we need to get the rate of the cord. So that would be ds over dt. So using Pythagorean theorem, we have x squared plus y squared. So that would be 60 squared equals s squared. Differentiating now with respect to time. So 2x dx over dt. Derivative of a constant, so that would be 0 equals 2s ds over dt. What we need is ds over dt. So let's divide both sides by 2s. So we'll now have ds over dt is equal to 2x dx over dt over 2s. We can still simplify this one. Okay? So by dividing 2 and 2. So this would now be x dx over dt all over s. So let's substitute our given. Do we have the value for x? Not yet, but we can get the value of x from this equation. Okay? So from that, x is equal to s squared, the square root of s squared, which is given as 100. So that would be 100 squared minus 60 squared. So solving for this, we will be getting 80. So x is 80 feet. So let's now substitute this one. X is 80. Dx over dt is 8 feet per second. And then the value of s is 100 feet. So solving now for ds over dt, we will be getting 32 over 5 feet per second. Another time rate example. A conical cistern is 10 feet across the top and 12 feet deep. If water is poured into the cistern at the rate of 2 cubic feet per second, how fast is the surface rising when the water is 8 feet deep? Okay, so we have a cone. Let's draw the given cone. So we have a conical cistern. Okay, so if it is a cone, it is given as 10 feet across the top. So the diameter of the cone is 10 feet. So if we're going to get the radius of that, so the radius is 5 feet. Okay, so this is 10 feet. Next, 12 feet deep. So the height of the cone is 12 feet deep. So if water is poured into the cistern at the rate of 2 cubic feet per second, so that is the rate of the volume, how fast is the surface rising when the water is 8 feet deep? So we need to get the value of dH over dt. So if we're going to pour water into this one, so there would be some water at this point. We don't know that height, so let's designate that as R. We don't know also the radius, so let's designate the radius as R. The height would be as H. Okay, so let's now identify the unknown. How fast is the surface rising? So we need to get dH over dt. So the volume, the rate of the volume is given. So we will be needing the rate of the cone, the volume of the cone. So base area times height. So we have 1 over 3 pi r squared times h. So that would now be the volume of the cone. But you can see that we have two variables. So we'll just be needing one variable. Okay? So we can express r in terms of h or h in terms of r. So let's use similar figures. So with our given bigger triangle, the radius is 5 since the given is 10 feet across the top. The height is 12. For the smaller triangle, this one, we have r and then height would be h. So using ratio and proportion, 5 over 12 equals r over h. If we want to solve for the value of r, so what would be the value of r? So 5 over 12 h. So let's substitute this one to our equation. So 1 over 3 pi, the value of r is 5 over 12 h, and then square that times h. So what would now be the value of this? Okay, so let's have that one. Let's simplify. 5 over 12 quantity squared is 25 over 144. And then times 1 over 3. So we will be getting, for the equation of the volume, 25 over 4, 32. Pi h cubed. So this is now our working equation. Okay, so from that, we can now differentiate this. What would be the derivative of this with respect to time? So dv now over dt equals 25 over 4, 32 pi. And then h cubed is 3h squared dh over dt. So simplifying this, we will be having 25 over 144. So 25 over 144 pi h squared dh over dt. And this is equivalent to dv over dt. What we need is the value of dh over dt, so divide both sides by this factor. So which is now dv over dt all over 25 over 144 pi h squared. So let's now substitute. dv over dt is given as 2 cubic feet per second. So we have 2 all over 25 over 144 pi. And the value of h now, what is the value of h when the water is 8 feet deep? So we have 8 squared. So solving this now, we will be getting the value of 9 over 50 pi feet per second. Let's have an example for a ladder. One end of a ladder 30 feet long slides down a vertical wall, while the other end moves away from the wall horizontally at a rate of 3 feet per second. How fast is the top of the ladder descending when its foot is 16 feet from the wall? Find the rate at which the area of the triangle formed by the wall, the ladder, and the ground is changing when the foot is 16 feet from the wall. So we have a wall, and then a ladder is leaning on the wall. So we have its top and its bottom. The length of the ladder is 34 feet. So the length of the ladder is constant. So let's designate this vertical distance as y, the horizontal distance as x. So one end of the ladder slides down the vertical wall. So it means that the top of the ladder slides down the vertical wall, so the value of y is decreasing. So we'll be having a negative rate of change. So since this would be descending, then the bottom of the ladder would be moving away from the wall. So we'll be having a greater value for x, so a positive value for x. So the rate of y is dy over dt, and the rate of x is dx over dt. Okay. So what would be the unknown? Find the rate of the top of the ladder descending. So we have dy over dt when x is 16 feet. And then another unknown is what would be the rate of the area. So dA over dt again when x is 16 feet from the wall. Let's have our given. So we can solve this using the Pythagorean theorem. So x squared plus y squared equals 34 squared. So differentiating now with respect to time. So 2x dx over dt plus 2y dy over dt, and then this, since this is constant, so the derivative of that is 0. We need the value of dy, so we will transpose this one on the other side. It would become negative. And then divide both sides by 2y. So we can now have dy over dt, which is negative 2x dx over dt all over 2y. And we can still simplify this one. Okay? So negative of x dx over dt and then all over y. So what is the value of x? X is 16 feet. We have the length of the ladder, which is 34 feet. So we can now solve for the value of y. So solving for y, we will be using this equation. So y is equal to the square root of 34 feet squared minus 16 feet squared. So from that, the value of y now is given as 30 feet. Let's substitute that. Negative x is 16. Dx over dt, it is given as 3 feet per second. And then the value of y is 30 feet. So solving for this, we will be getting the value of dy over dt, and the value of that is negative 8 over 5 feet per second. Another unknown is dA over dt. So since it is a triangle, we can solve for the area of that. So the area of a triangle is 1/2 base times height. Base is x and then height would be y. So dA over dt, product rule, we have 1/2 x. Derivative of y is dy over dt plus 1/2 y. Derivative of x is dx over dt. So let's substitute now. 1/2 x is 16. We already solved for the value of dy over dt, which is negative 8 over 5 feet per second plus 1/2. y is 30, and then dx over dt is given as 3. Okay, so solving for this, we can now compute the value of dA over dt. And dA over dt is 161 over 5 square foot per second. A triangular trough is 12 feet long, 3 feet wide at the top, and 3 feet deep. So if water is poured into the trough at a rate of 10 cubic feet per minute, find how fast the surface is rising when the depth is 2 feet. So we have a triangular trough. So let's draw the given. So we have a trough in the form of a triangle, and it is 12 feet long. So it is 3 feet wide at the top, so this is 3 feet, and 3 feet deep, so the altitude is 3 feet. Now if water is poured into the tank or into the trough at a rate of 10 cubic feet per minute, so definitely we'll be having water. And then we have to identify this. We don't know this one. Let's designate that as B. That would be the base. And then the height of the water is H. So how fast is the surface rising? So we need to solve for dH over dt. Okay? So the rate of the volume is given. So we will be using the formula for the volume. So volume is base area times height. So the base is a triangle. So 1/2 base times height, and then times length. Length is 12. So this is now 6b times h. But since we have two variables, we just need to express the volume in terms of one variable. So it could be base b or it could be h. So by using similar figures from our given, so bigger triangle, this is 3, and then height would be 3. Smaller triangle, from the given figure, we have base and height. So by using ratio and proportion, 3 over 3 is equal to b over h. Okay? Now, if we want to get the value of base, we can get that from here. Okay? So 3 over 3 is 1. So base is equal to h. So let's solve for the value of b. B is h. So v is equal to 6. The base is h, and then h. So this is 6 h squared. So we can now differentiate this one. Let's differentiate with respect to time. So dv over dt is equal to 6. Derivative of h squared is 2h, and then dh over dt. What we need is dh over dt, so let's now solve for that. This is equivalent to 6 times 2, that would be 12 h dh over dt. So we'll divide both sides of the equation by 12h. So dh over dt now is given as dv over dt all over 12h, and then substitute the given. So the given for dv over dt is 10 cubic feet per minute, so that would be 10, and then 12. The given height is 2 feet. So this is 10 over 24. Okay? Or 5 over 12 feet per minute.
Lesson 4 for polynomial curves. The derivative of a function and it is merely the slope of the tangent line to the curve of the function at any point xy on the curve. Now consider finding the equation of the line that is perpendicular to the tangent line at the point where it touches the curve. The tangent line to the curve with equation y equal f of x at the point p sub 0 with coordinate x sub 0, y sub 0 is the line through p sub 0, x sub 0, y sub 0 with slope f prime x sub 0. Recall to the point slope form for the equation of a line y minus y sub 0 equal to m multiply x minus x sub 0. From y minus y sub 0 is equal to m multiply x minus x sub 0, and taking m equal f prime x sub 0, the equation of the line tangent to the curve at the point p sub 0 is equal to y minus y sub 0 is equal to f prime of x sub 0 multiply quantity x minus x sub 0. In this example, the normal line to the curve with equation y equal f of x. So you have the tangent line, the red line, and the normal line, the green line. At point p sub 0, x sub 0, y sub 0 is the line through p sub 0 which is perpendicular to the tangent line at p sub 0. So this is the point of p sub 0. Okay. If the tangent line with slope m sub 1, let's say this red line with slope m sub 1 is perpendicular to the normal line with slope m sub 2, the green line, the relationship between the two slopes is m sub 2 is equal to negative 1 over m sub 1. So in this slide, these are examples 1 to 3. Next, a function is said to be increasing in the interval if the value of y increases as the value of x increases. In this example, from point A to point B, the value of y is increasing as the value of x is increasing. Okay, so from the interval A to B, you have the value of x increasing while also the value of y increases. It is said to be decreasing if the value of y decreases as the value of x increases. In point B to point C, you have the value of x increasing, okay, the value of x moving from left to right, while the value of y is decreasing. Okay, so y is decreasing. Consider the curve y equal f of x in the figure on the closed interval a to b. Closed interval a to b, okay, this is the interval. The value of y increases as the value of x increases. Notice, as x increases, y is increasing. Hence, the function y equal f of x is said to be increasing on the closed interval a, b. On the closed interval bc, y decreases as x increases. The function y equal f of x is said to be decreasing on the closed interval b to c. Okay, so this is the interval bc. Notice the value of y decreases as the value of x is increasing. Next, on the closed interval cd and de, y increases as x increases. Notice between this interval cd, as x increases, y increases. Also, for d to e, the value of x increases and also the value of y increases. So, the function y equal f of x is increasing on the closed interval c, d, and d, e. Another method to determine whether the function is increasing or decreasing is by examining the derivative of the function or the first derivative, the slope, y prime. At any point between a, b, so this is point A, point B, between C and D, this is point C, point D, where the function y equal f of x is increasing, the slope of the tangent line is positive, or the derivative, first derivative, f prime x is greater than 0. Okay, so if you have a slope that is greater than 0, the slope is leaning to the right. At any point between B and C, this point B and this point C, where y is equal to f of x decreasing, the slope of the tangent line is negative, or the first derivative f prime x is less than 0. Okay? If we have a negative value for the first derivative f prime x, then it is said to be decreasing because the slope is leaning to the left. At point BC, point BC, at point B, point C, and point D, the tangent line is horizontal, or it is equal to 0. The slope f prime x is equal to 0. So the line or the slope of the line is horizontal. The point where the tangent line is horizontal or f prime x is equal to 0 is also called a critical point. So the critical points in this example, point B is a critical point C is a critical point, and point D is also a critical point. Identify the interval of the function, whether it is increasing or decreasing. Next, critical points are points of which y prime is equal to 0 or f prime x is equal to 0 or the slope is equal to 0. So you have a horizontal tangent line. Maximum point. Maximum point is where the curve changes from increasing to decreasing function, meaning the slope changes from positive to a negative sign. Minimum point, point where the curve changes from decreasing to increasing function. So the minimum point you have from decreasing function, the slope is negative, then changes to increasing function, the slope is positive. So you have a minimum point. Consider the graph y equal f of x. From the figure, point B, point C, and point D are critical points. B is a maximum point, C is a minimum point, while point D, it is neither maximum nor minimum. You cannot determine if point D is a maximum, if point D is a minimum, but it is neither maximum nor minimum. Between point A and B, since f prime x is greater than 0, at B, f prime x is equal to 0. So at point B, it is equal to 0, a critical point. At point C, f prime x is equal to 0. So you have another critical point. And point D, f prime x is equal to 0, another critical point. Between D and E, f prime x is increasing, or the slope f prime x is greater than 0. The first derivative test. So the first derivative test, from the word first derivative, you need to determine the first derivative. Then, at point where y prime is 0, if y prime changes from negative, okay, the slope changes from negative to positive, meaning leaning to the left, then changes to leaning to the right with regards to the slope. As x increases, y is said to be minimum. If y prime changes from positive to negative, as x increases, y is a maximum. And if y prime does not change sign from, let's say, positive leaning to the right, then after the changes, it is still positive sign, then it's said to be neither maximum nor minimum. So y prime does not change sign. Here are some of the examples for first derivative test. A point is said to be a minimum point if you have the slope y prime changes from negative sign to a positive sign. Okay, so you have a minimum point. So this is, if you have a line here, tangent line, it is leaning to the left. If you have a tangent line here, it is leaning to the right. So notice the blue line. In this example, maximum point, you have the function changes from increasing, then changes to decreasing function. Okay, with regard to the slope changes from positive to negative. Then you have a maximum point. For these two examples, if you have the tangent line or the slope f prime x is greater than 0 or it is positive, then after the interval, you still have another, the sign of your slope is still positive, then it is neither maximum nor minimum because your the sign of f prime x did not change from positive still to positive. In this another example, the sign changes from negative to negative, leaning to the left. Then after the interval, you still have leaning to the left, where f prime x is still less than 0, then you have neither maximum nor minimum. So in this example, applying the first derivative test to determine the maximum and minimum values. I will show you the solution for these problems in the succeeding slides under Canvas. Concavity. Second derivative test. Consider again the graph of the function y equal f of x. So if you have point A, point B, point C, point F, point G, point D, and point E. Okay, so notice for point A, point F, and point G, solving for the second derivative y double prime, okay, you have the values y double prime equal to 0 at point F, y double prime equal to 0 at point G, y double prime is equal to 0. Later on, I will discuss to you what are the significance of the points. The part ABF of the curve is concave downward. ABF, concave downward. While the part FCG, the curve is concave upward. Okay, so notice for the concave downward, you have a maximum point. For concave upward, you have a minimum point. Second derivative test. Y equal f of x is maximum at x equal a if f double prime a is negative or f double prime a is less than 0. If y equal f of x is minimum at x equal to a if f double prime a is positive or f double prime a is greater than 0. So this is how you determine the maximum and minimum point using second derivative. The test will fail if f double prime a is equal to 0. If your f double prime a is equal to 0, it means that the point is neither maximum nor minimum. Point of inflection. A point where the curve changes from concave upward to concave downward and vice versa. Okay, so again, as I mentioned, point F, and G, where y double prime is equal to 0, are called the point of inflection. In this example, determine the maximum and minimum points using the second derivative test. Also find the points of inflection. Sketching polynomial curve. This is also one of the application of first derivative, and also if you will use the concavity to solve for the second derivative to determine the maximum and minimum points. So the steps are: find the points of intersection with the axis or x and y intercept. So if you have the x and y intercept, determine the value. Number 2, determine the behavior of your y for large values of x. So you assign a value for x, a large value of x, then determine the behavior of y. 3, find the critical points and classify the maximum and minimum points. Number 4, determine the point of inflection. 5, locate the points of the graph and plot a few points. And finally, you can sketch the curve. Example 7 and 8, sketch the curve of the function.